Ooh, flower. So there's this CalcPlot 3D that I told you guys about. There's a link on one of the discussion threads, and there is a downloadable Java applet that you can run. So to graph three-dimensional curves using this program, you go to, I took out the box by view settings. So view settings allow you to format the axes and the boxes and whatever else you need to format. You can go to the graph, and it says parametric or space curve. It says space curve. And here's cosine, sine, and some number times t. So this is that helix thing that we were talking about. And if we were to graph this t goes from negative 10 to 10, by the way. And if we graph it, we see a spiral. And so you can adjust the way they color things. They color it according to the height. And then you can ask it to trace for some t values. And what you would get there is a drawing vector, a vector that draws from the origin to the position. So this is essentially the position function vector that's drawing out your curve. It shows the orientation as well. It's supposed to. I'll show orientation. It tells you, because a curve is a curve, right? But the vector valued function draws the curve in a specific direction. So the arrows tell you which way this is going. If you look at it from the top, it looks like it's going counterclockwise, and it's increasing as you go up. So that's what the arrows tell you. You can show one arrow or a bunch of arrows. You can have it trace. Use primary colors. So Sarah, there you just have one color, and then you can add another graph here if you want. So we can add another space curve. So space curve number 2. This time let's draw .5 times that. 0.7 times that. So we're going to draw a smaller circle, and then let's see if the colors are going to be the same. Now it's still going to be red. So, and then after you draw it, you can move this around so you can view it from different angles. And then you can remove a graph if you want, so you could just focus on one of them. Restricted to 2 dimensions. Let's do this one. And so this is the view from the top, and this is what you would see if you were to look at it from the top. Okay? So you can control the tracing, the animating by this, so you can see exactly where it's going at any particular point t. Okay. If you go on the, I don't know if this is the same book. Sometimes there's some links in the online book where you can click on something and then it might pop up a Mathematica page where you might be able to view some sort of animation. I'm not sure if that's, I've seen things like that before, but I forgot if it was this book or a different book. But you can check, they do have Mathematica support where they can show you things that were built in Mathematica, but you don't need Mathematica to run it.
Is that the link of the e-textbook on the website?
Yeah, yeah. So the e-textbook on WebAssign might show these things as well. But it'll be really restrictive because it'll just say these are your 2 types of functions that you can select, and if you choose this function, this is kind of things that you see. With this program, you get to put in your own function. So I had some, I think in my notes I was going to give some examples. Let's do, well, the first one was a helix. We already talked about that. And the second one, let's see if we can graph that one. So from last time we talked about this example. Well, where it's a helix. So let's see if we can graph this other example. Trying to graph parametric equations in 2 dimensions is kind of tricky already, but we did that exercise at the very first day of class. But trying to graph things in 3 dimensions, that could be really difficult. So I would suggest for you to just put this in a computer program and see what you get. So that's what we'll do. So we've got t squared, t to the 4th, and t to the 6th. So x is equal to t squared. Y is equal to t to the 4th, and then the third one is t to the 6th. Oops. And then we can start off with -1 to 1. We go from -10 to 10. Maybe we'll start off with -1 to 1 just to get some idea first. So with these polynomials, you can see it gets kind of difficult to try to imagine how these things would look like. So it might be good to take a look at the tracing. So at -1, you're being pointed over here somewhere, and then it goes down to 0, and then it goes up. Oh, it goes back. Oh, what was the other picture? So this looks like it's drawing the same thing. Let's go -3 to 3. There it goes. Now it goes up a lot higher. So the animation starts up high wherever that is, and then comes back to 0, and then goes back out. For this, if you want to change like the viewpoint or the limits for the x, y, and z go from -2 to 2, it looks like. So I might be interested in seeing this up higher in the z-axis. So you can change the axes, the limits for the axes. You know how we change the max and the min on the calculators, x max, x min. And we could do the same thing here. We could change the z to maybe go from -1 to the maximum of, let's maybe go up to 15 for now and see what happens. So if we apply the changes, you kind of see it a little bit more compressed, and then you can try to follow this animation again to see how the graph is being drawn. All right.
Sorry, does that mean it just repeats itself?
Yeah. Well, it looks like because they're all even number squares, it's going to be symmetric in all the axes. So it looks like it's going to redraw itself. In fact, if we draw some arrows, show some arrows, arrows look like it's the same thing that's being drawn there and back. So I don't know if this was a good example in terms of getting a visual for this, but it's when you see polynomials tend to go off to infinity eventually, and so when it goes off to infinity like that, it's harder to well, you can't contain it, but you'll see things shooting off to infinity. So the more interesting graphs might have to do with, some of them might have to do with sines and cosines. Yeah, Matt. Well, you can track a projectile moving through space. You know how you can watch a ball in 2 dimensions and graph that. This time you can track something in 3 dimensions. So we can do it in 2 dimensions as well. In fact, we'll do a little bit of that. We'll bring this back down to 2 dimensions again and then re-extend it to 3D. And maybe by the end of today, I'll walk you through my thinking process when I'm writing exam questions. All right. So that's the basic idea with vector-valued functions, and all they ask you to do in this particular section is to graph it and match graphs and equations and stuff. So just get one of these programs and then graph it and see how it looks like. All right, let's move on to the next section, which is taking derivatives of these things, derivatives and integrals, really. So find derivatives of vector-valued functions. We want to find the unit tangent vector. The unit tangent vector will help us begin to provide a frame for our graph a little bit later on. Tangent lines. Now we can really talk about tangent lines in space, and then find integrals. Definite integrals and indefinite integrals. So those are our basic ideas. So start with a derivative. I'm going to throw up a derivative formula, definition that they have in the book, which is your standard derivative definition. But we won't dwell too much on the definition itself because really we're just going to focus on being able to take derivatives, and you guys are all experts at taking derivatives already. So the main idea behind this is that the derivative is the same derivative formula where you have the limit as h approaches 0 and stuff like that. And so I think if you look at the textbook, you can get a nice visual on this idea of a derivative that's applied directly to the curve, to the space curve. But the bottom line is that to take the derivative of a vector-valued function, you simply take the derivative of each of the components separately, which makes it really, really, really nice and easy for us to deal with. So let's take that example that we have, or that we had. I think r of t was equal to, t squared, comma, t to the 4th, comma, t to the 6th. And so the derivative of that is really 2t 4t cubed 6t to the 5th. So that's all there is to it. Right? So that's the easy part, is just doing the mechanics. But on top of that, let's see if we can start applying this idea to a space curve. Oh, by the way, this is the tangent vector at any point t that we choose. So if we fix a particular t value, then if we put that t value in there, we're going to get the tangent vector at that point. Yeah?
So the 2t, those are the times of each of the axes?
Oh, the 2t? This 2t?
Yeah, and like so like that's 2t is the time.
So, well, it's actually the function now. It's the rate of change of the function in the x component, the rate of change of the function in the y component. Okay. So it's kind of aside from its simplicity, I think it's better to look at this idea as a whole instead of looking at the little bits and pieces. And so let's get to my thought process in making up a problem. I like the idea of using things like roller coasters or baseball games or things like that to represent in vector valued functions. And so let's just imagine you had a simple roller coaster where in 2 dimensions from the top it just goes around in circles. But as it goes around, it kind of loops, right, up and down. So that's a fairly simple kind of roller coaster. Well, let's come up with a function that represents something like this. So if this is just going to go around in circles on the x and y, what can the x and y be? So the sine and cosine, right? And if I want to give it a radius, we'll have an appropriate radius for that. So let's go with radius of 5. Oh, it doesn't have to be a circle either. We can make it just a little slightly elongated in one way. So if on the second one, instead of saying 5 again, 5 sine t, maybe I'll change that to 7. The combination of sine cosine will get you the circles on the x and y. So, right?
Yes.
And so it was one of the first things that we did, and now that we're talking about vector valued functions, we're going to keep coming back to that. And so that was an important first example for parametric equations, and now in vector valued functions, it'll be the same thing. Now, if I just had a t here, remember it's going to be that helix that's going to go up, or some constant times t. It's going to be some helix. But I want it to oscillate. So we're going to use another trig function. So we'll use sine or cosine. Let's use sine. Now, if I say sine t, then it's going to have the same period as a circle, and so this is just going to go in one loop back. So to make it a little bit more exciting, maybe we can have it loop a bunch of times before it gets back. So we could do 2 or 4, just some other constant over here. And then the height over here, we can adjust the amplitude. So let's do maybe 4t. All right, so I'm going to take my simpler graphing program and then graph that. It's simpler in some sense, but you have to know the kind of the syntax. So the syntax for this particular program uses vectors. So the x, y, z vector is equal to, and then you got whatever it is you're going to do in x, y, z. Let's see, that doesn't look exciting. Yeah, so right now it's going from 0 to 1, so it's only going to give me 1 radian's worth instead of 2 pi, which is what we normally do. So let's go 2 pi, and then we get that. It looks kind of wavy. All right, so here's our graph so far. I think that's a nicer picture than the one I had, so I'm going to change my picture. And maybe we should make it a little bumpier. Sorry, I'm going to change it. Somewhat. I don't want to get too crazy now. Let's try multiplying this by 6. A little too much. 3. Is that okay? 3 or 6? 3. 3 looks nice. All right, I'll go with 3. Let's put this in our notes. Now let's take the other one out. I don't think it makes a difference. Okay. So this is a position. This tells us the position. Actually, I think it would be good to see that drawing vector going on. And so there's a little trick for this in this program. I can define a variable that I'm going to be changing, and then I'm going to recreate this function by a vector. Yeah, so t is going to equal to a, so I'm going to change all the t's into a's, but I'm going to change, I'm going to make a vector going from the origin. So this is going to be a vector in standard position, and going to the position where I have the function evaluated at some a value. So it's going to point to somewhere on that curve. So if you look at this and you take a look at that, there's a drawing vector that draws out your position in the roller coaster. Okay? All right. So that's the position vector, and we'll call RT our position vector. Now let's go ahead and take the derivative, since that's what we were just talking about. Let's take the derivative of this thing. R prime of t is equal to, I think derivative of cosine is negative sine, right? So negative 5 sine t, it's positive 7 cosine t. And then here's a chain rule, so drop that 4 out, and then sine is, derivative sine is cosine. Oh, 3. Changed it to 3. So this is 12. All right. Now, this vector Now, first of all, we have to acknowledge that this is a vector-valued function, so this is a vector function. But the significance of this vector is not a vector in standard position. All right? So this vector is the derivative vector, but more significantly, in terms of this vector-valued function, if we look at the vector-valued function as a position of some particle, or your position in a roller coaster, and if we look at that as our application for this vector-valued function, then this derivative becomes the velocity. It's what? If you take the second derivative, it'll be the acceleration. So now we have a velocity vector, and like I was trying to say, the velocity vector is not very useful as seen from the origin, as seen as a position vector. Okay, so what would be interesting is to actually see this being applied now is to take a look at this velocity vector at some value. So let's take a look at the velocity vector at, let's say, t is equal to 0. So we say r prime of t, or r prime of 0, we'll put 0 in a minute. Oh, we'll put 0 in now because we already have the derivative. What's sine of 0? 0. Cosine of 0? 1. So this is 7 times 1. And then cosine of 0 again is 1, so 12. So now I'm looking at the vector 0, 7, 12. And so like I said, from the origin, this is not very significant.
If you put the vector at
Say it.
you put the vector at the point to which it corresponds.
Yes.
Would the direction be the
Yes.
same time?
Yes. So this is the velocity at t is equal to 0. If we take a look at r of 0, let's put 0 in for r, or 0 in for t in the r function. We have cosine of 0, which is 1, sine of 0, which is 0, and then sine of 0, 0 again. So at 5, 0, 0, you're currently at that point. So if we look at this as a vector, then that's not a vector. If you look at this as a vector, then you would have a vector from the origin pointing to that point. But it's actually better to look at this as a point because this r is actually a position. So it'd be much better to look at that as a point. Now, if you take r prime and take it out of the origin, take it out of standard position and move its tail to where this point is, you're actually going to get a vector that's tangent to the curve. And that's the beauty of this derivative, is that it really gives you all the components for your tangent vector, and it actually does give you a tangent vector. Okay? Does that make sense?
So the position is the point, and then you take the derivative of that, the tangent vector.
Yes. Yes. So the velocity vector, we call it a velocity vector, but we can also call it a tangent vector, yet another name for this. because it literally will give you a vector that is tangent to the curve at that particular point. Okay? So I'm going to create this vector in my drawing. And the way to create this is that when I do vectors in this program, I need my tail first and then my head. So my tail is the position vector, and my head will be the position vector plus the velocity vector. So I need to take that derivative. So we did this already, right? The derivative vector is 5 sine t, negative 5 sine t, 7 cosine t, and then 12 cosine. So now if I move my slider around, I'll see that as I move around my curve, my velocity vector is always going to be tangent to that curve. Okay? Well, the way this program works, it always would draw the vector from tail to the head. So if I want it out of standard position, I would need to add the tail to it, and I would need to add the tail to the head too, because it's going to be a new head. So otherwise it'll look a little strange.
That's why you would have it.
Yeah. Yeah. Okay. So we're going to get tangent vectors. The acceleration vector is not that meaningful in terms of a vector graph to it. But if you're going around in a circle, do you know the idea of where the acceleration vector should go? It's going to go towards the center. It's going to pull in towards the center. So we'll see that if we found the acceleration vector, it'll be, well, let's find the acceleration vector. So the acceleration vector, we'll call it r double prime of t, is going to be the derivative of the velocity vector. So sine is positive, so this is already negative. Negative 5 cosine t, negative 7 sine t, this is a negative, and then whatever this is, 48. Negative 48 sine 4t. So the z is going to do whatever the z is going to do, but if you look at the x and the y, compare it to the position function, it's going in the opposite way. It's like the position function going in the opposite direction. So you can see that centrifugal force pulling back in. So that's your acceleration. And if we do want to see it, we would graph this velocity or this acceleration vector starting from the position instead of starting from the origin, if we're interested in looking at it. All right. Any questions?
Is it safe to say that the x and y for most functions, if you take the second derivative, will always be the opposite function?
No, only for circular things. Yeah. All right, so as you can see, when I'm looking at my graph over here, that velocity vector looks kind of long. There are some cases where we might just be interested in the direction of the velocity and not the length of the velocity. So this would be a good time to think about making it into a unit vector. So let's make this into a unit vector. Yeah. So the unit tangent vector is defined to be the velocity vector made into a unit vector. Now, the velocity vector is a function of t, which means we can generalize this for any t value that we put in. So we want to have the unit tangent vector as a function of t as well. And really, the formula for this is that we'll call it capital T of little t is equal to, how do you make something into a unit vector again? Divide by its magnitude. So you get the velocity vector, which is r prime of t, and then you divide by its magnitude. So in terms of symbols or formulas, that's pretty easy, right? It's about as easy as it gets. But now to actually apply it, that could be a little bit more difficult. And messy, I guess, is the word for something like this. So in our example over here, so the unit tangent vector in our example is essentially going to be this vector divided by the magnitude of this vector. So the magnitude of this vector, we have to do that big thing where we square it and stuff. So that's where you get this messy answer. So the vector itself is just negative 5 sine t, 7 cosine t, 12 cosine 4t, and then 5 sine t squared. I guess I'm not going to simplify this. If it was a nice helix, circular helix, or if this was circular, if I didn't change the 5 and 7, if I kept that the same, this would have simplified just a little bit so it could look a little nicer, but I didn't. I changed it, so now it's a big mess and I won't be able to simplify it. So there are times when the velocity vector, goes, extends and stuff like that. In case we just want the direction and we don't care about the length. And we'll talk about the length of this tangent vector too. That's a significant aspect of what we need to know. Anybody done arts, animation, and stuff like that? Robotics? Robots flying through the air? Did you guys do? If you do robots flying through the air, when a drone is robotized, not that you're controlling it, but your drone is moving on its own. What? Autonomous, making it go through hoops and stuff like that. At any instant in time, your robot is some point in space, and at that instant in time, your robot needs a frame for itself to determine which way to go. It's not always going to rely on the origin being an origin where it took off from, right? So at any point in time, it needs its own origin. It itself is its own origin. So it defines a three-dimensional space from where it is at any point in time. And so at that point in time, it defines a set of vectors that tells you which way is forward, which way is left, and which way is up. Okay? And what that does, it creates what's called a frame for the robot to go. And so we want that frame to be as simple as possible, which means we want those vectors to be unit vectors. We want those vectors to be perpendicular to each other. And there's a special name for that. It's called a Frenet, F-R-E-N-E-T. We'll talk about that in a couple of lectures from now. But that Frenet frame allows you to create a three-dimensional space of reference for that drone. All right, so if I was to graph this, let's continue working on our picture. If I think that this graph is too long and I want something a little smaller to deal with, then I could just multiply this by, or divide it by the thing. I don't know if I want to do that. Nah, I won't do that. By the way, in this particular example, it looks like does it look like the length changes? I can't tell. It looks like the length might be changing, yeah? Okay, so we just took out the idea of the length of the velocity vector, but the length of the velocity vector actually is an important thing. So it turns out that the length turns out to be the speed. Now, when you guys used to do these projectile problems in Calc 1, maybe Calc 2, you toss a ball up in the air and you figure out how fast it's going and stuff. The velocity vector told you the speed. And then, if you remember, sometimes you would get a positive number, sometimes you would get a negative number, depending on how you set your gravity. So, when you threw a ball up in the air, I guess I should draw you first. Throw the ball up in the air. When it goes up, it has again, your gravity is going down, so depending on how you set your positive and negative, this would be a positive velocity and this would be a negative velocity when it comes down. So in this scenario, you only have two directions, and the velocity gives you a scalar value. But when you're moving in 3D, I guess I should try to draw you in 3 dimensions. And then you throw this ball it turns out that your velocity now is a vector. So the whole idea of positive and negative doesn't quite make sense in terms of just saying plus and minus. So it's a little bit more complicated than just having a plus for going up and minus for going down. But it holds a lot more information than just a scalar. You actually get the direction of the ball, the direction that it's moving, but not only that, the length. Is actually telling you how fast it's going. So over here, as it starts leveling off, your ball might slow down a little bit. So your velocity vectors will be a little bit shorter then, and then when it starts going back down, your velocity will start going faster again. So it turns out that the magnitude of this holds a lot more information than just a scalar going up and down, positive and negative. All right? So we can ask ourselves, if you're on this roller coaster, do we actually define this to be a roller coaster? No. So we can ask ourselves something like, how fast are you going when x is equal to pi? So let's say pi is over here. I guess that's the x. Yeah, that should be pi. You should be over here. So what do you need to do? You need to find r prime. So what was r again? R was... So to find out how fast you're going, you need to take the derivative. Negative 5 sine t, 7 cosine t, 12 cosine 4t. Boy. And you could find the magnitude now, or since you have a specific value of pi to put in, maybe you might actually be better to put pi in first and then take the magnitude, because if you put pi in, then you're just dealing with numbers. So let's find out what r prime of pi is. Sine of pi, 0, negative 1, 4 pi, positive 1. Is that right? So now this is easier to find the magnitude. Square root of 49 plus 144, which is whatever. 195, 193. Okay. So whatever value this is, whatever units, I didn't put units, meters, feet, whatever. This is how fast something's going. Okay. All right. So another interesting problem that we can come up with a projectile moving around in space like this would be a tangent line. Yeah.
Is it when t equals like time?
Yeah. Yeah. When time is equal to pi. Oh, that should be t, huh? All right, so the other idea is to try to look for a tangent line. We dealt with lines and planes, so we know how to deal with lines and planes already, and so we can deal with tangent lines. So let's deal with tangent lines. What do you need for an equation of a line? Slope and derivative? What? No. What do you need for an equation of a line? We spent like 2.5 days. Point in a direction vector. Need a point and a direction. What's your point? Given point. So let's say you're on this roller coaster, and at some point in the roller coaster you get ejected and you go off a straight line, right? So you go off in a straight line because you're in space, and when you get ejected you don't have gravity pulling down. So you go off in a straight line. What point did you leave? Do you understand what I'm asking? Yeah? The point at which you were ejected, which is a point on the curve, right? So how would I express that point on the curve? Let's say you got ejected at time t is equal to t naught. R of t naught. Does that make sense? R is the position vector. R of t naught puts you at that point on that curve where you might have gotten ejected. What's your direction? The tangent vector, right? The tangent vector. So your direction would be the tangent vector. I'm mixing up my colors now. My colors aren't consistent anymore. So that's it. All right, so let's say you were on this roller coaster, yeah?
So R of t naught,
Mm-hmm.
is the point at which we're ejected from, and our time is how fast we're ejected from that state.
Not only how fast, but the direction. The magnitude of it is how fast, but the direction, which is what you want for the tangent line, the direction tells you which direction you're going. And so if you're over here, if you're on this roller coaster and you got ejected at t is equal to pi, then you're going to get ejected in the direction of the tangent, and so you're going to be on this line going at whatever direction that you're going. Yeah. Question?
Is that line like consistent? So are we going to, assuming that we're in space, that's where we're going to go in the same direction all the time?
Yes. Yeah, technically it wouldn't make sense to go backwards, but the line that you described can go backwards if you want to look at it backwards. But in terms of a word problem or something, it's going straight ahead. Yeah?
The tangent vector gives you the directions.
Yes.
The magnitude divided by the time.
Is a unit tangent.
Unit.
Yeah.
And then the magnitude is how fast.
Yes, the magnitude of the direction, the magnitude of the tangent vector gives you the speed, how fast it's going. So I think we did all this stuff already. Let's in our example, Am I going to keep writing this down? Is it 5 cosine? And then 3. So I'm not going to do all the work. Let's just get the r prime, or r of t, or r of pi. We want it at pi. So r of pi is equal to, I'm going to put pi into the original r equation. Cosine of pi is -1. Sine of pi is 0. And 0. So that's my position. I'm -1 and -5 in the x, 0 in the y, and 0 in the z. So that's this point right here. And then my direction vector for my equation of the line is a derivative evaluated at pi, which was what? Do you guys remember what it was? 0, 7, 12. -7 or -12? -7. Okay, so if we want to find the equation of this line, let's call it L for line, and then it's just going to be -5, 0, 0, plus t, a different t, a new t, times 0, -7, 12. And if you want, you can change this into symmetric equations, or you can change this into parametric form with 3 equations, x, y, and z, or you could just leave it like this. Yeah?
Will we be expected to write in that form unless otherwise specified, or is it?
Yeah, I think this is the simplest form, I think. So if it's not specified, I would leave it like this. If it specifies for you to write it in symmetric equations, then you would need to write it in symmetric equations. But if it's not specified anywhere, I would be done with this answer. Okay. Okay, so just to end this particular example, let's say this roller coaster was in a room with walls. And you get ejected. And so you're going to fly off in a tangent line. And you would expect it to hit the wall somewhere. And let's say you had a Velcro suit on. So let's formalize this as an actual problem that I've given in my exams before. Suppose you were on a roller coaster given by r of t equals whatever that was, 5 cosine t, 7 sine t, and 3 sine 4t. You get ejected into a straight line at t equals pi. There are walls around this coaster at plus and minus, and let's just say So I need 6 walls, really, 6 walls, a floor, and a ceiling. So at planes, and then I'll just say x equals plus and minus 12. Y equals plus and minus 12. I'll just say x, y, and z. So imagine this. There's this thing is in a box now, right? Which wall would you hit and where? So we've established that you go off on this with a tangent line given by L of t is equal to, what was it? Minus 5? Zero, -7, and 12. So, intersection, you're going to hit a wall, right? So this is going to be some sort of intersection. So this looks like it's going to be -5 plus 0t, 0 minus 7t, and 0 plus 12t. So these are your x, y's, and your z values. And what you would do is to find an intersection, you would find some appropriate way to set two things equal to each other. And you know that x is equal to 12, x is equal to -12, y is equal to 12, y is equal to -12, z is equal to 12, z is equal to -12. So out of all those 6 options, what would make sense for you to be able to solve for something? So x is equal to 12 or -12 wouldn't make sense. That wouldn't make sense because x is equal to -5. So y is equal to 12 equal to 7t, -7t. So what are your possibilities here? T equals so t is equal to -12 over 7, which is negative. So that doesn't make sense either, right? Because you'd be going backwards in your line. So how about t is equal to -12? Y is equal to -12 over or y is equal to -12, which is equal to -7t. So here t is equal to 12/7. Okay, so that's a good candidate that you're going to hit the y is equal to -7 wall. Yeah.
The -12/7 doesn't work.
Because we're looking at this line and we're moving forward in this line.
Oh, so you're going back onto.
Yeah, the -t moves you back. But it turns out that if you let z equal to -12, you're going to get something there too. Or +12. So it looks like there's 2 places I could hit the wall. I could hit the wall y is equal to -12, or the wall, I guess this is a ceiling, 7, or I'm sorry, z is equal to positive 12. So now it's going to be a question on which one I hit first. So 12 over 7 is bigger than 1, right? So this is bigger than 1, and this is 1. So it looks like at time unit 1, I'm going to hit the ceiling at z is equal to 12. I'm going to hit that. And at time bigger than 1, after 1, I'm going to hit the wall if I go through the ceiling. Okay? So which wall would you hit? You would hit the ceiling, and then where would you hit it? You would still need to find the x and the y values. So I'll let you think about that. Yeah?
So since that one's bigger, it takes more time.
It takes a longer time for you to hit the y wall.
So because that's bigger, you know, it's always smaller.
Yeah. Well, for this scenario, it's a smaller one. Okay? So this would be a typical problem that you would see on a test. Not exactly like this, but something like this, where it goes through a process of finding things and then using that to go to the next step. No, it's not. We're not done with this problem, but we're out of time, so. What? No, not yet. To find where? To find where? Yeah. To find where, you would need to figure out you need to figure out where the line is when t is equal to 1. So you put 1 in for t, and then you're going to get the x, the y, and the z components of that. And then that will tell you where. Okay.
You said it's 3 points each for the y minus 2.
Oh, this wasn't 3 points each.
Oh.
I stole this from an exam, and so in the exam I have point distributions. Sorry, I didn't mean. These are actually 2 points each.
Do you want this now? Or?
Give it to me next week.
Okay. Oh, also, so everything got confused. It's actually